operational amplifiers. So op-amp is a amplifier circuit. It is available in the form of IC as well. Okay, it's available in the form of IC. Okay, it is nothing but IC541. IC541 is the practical IC that is available in the form of op-amp. So op-amp operational amplifier. Okay, so amplifier in the sense it has to amplify the signals. In the sense I have some black box. So to that black box, if you give some signal which will be of low amplitude, it has to amplify it. It means that it has to improve the strength of the signal. It means that it has to improve the amplitude. Okay, so that is the reason it is said to be the amplifier circuit. IC541 is said to be the op-amp, which is nothing but the amplifier circuit. And along with the amplification, it will also provide some mathematical operations like addition, subtraction, differentiation, integration, like that. Okay, and this op-amp, it is not single stage, in the sense like I will not have only the single amplifier. It will be the cascading of so many amplifiers. Okay, so that is the reason it is said to be op-amp is said to be the high gain differential amplifier. High gain differential amplifier. How I am going to get a high gain? The high gain will be achieved because I will have so many amplifiers cascaded in this way. Okay, so that's why it is said to be the high gain differential amplifier. And coming to the differential amplifier, it is said to be the differential amplifier because op-amp, what it will do, it will not directly amplify the input signal. It will take the difference between the two inputs. Okay, so this is the non-inverting terminal. Plus is said to be the non-inverting terminal, and minus is said to be the inverting terminal. Okay, inverting terminal. So the difference between the two inputs will be taken and it will be amplified. Okay, so that is the reason it is the differential amplifier. High gain will be achieved because of the cascading of so many amplifiers, and it is said to be the differential amplifier because the difference between the two inputs will be amplified. So that is the reason it is high gain differential amplifier. Okay. High gain differential amplifier, and the symbol of the op-amp will be in this way. You'll have the plus, minus, and these are the two inputs V1, V2. It will always take the difference between the non-inverting input minus the inverting terminal input. Okay, so it will be like V1 is the non-inverting terminal input minus V2 is the inverting terminal input. So why it is called as non-inverting and why this is called as inverting? Why this is called as non-inverting in the sense like when you give input only to this non-inverting terminal, and if you try to calculate the output, the output will be in phase, in the sense like if I'm giving sinusoidal signal here also I'll have the sinusoidal signal only, but with high amplitude, in the sense like both will be in phase. So this is my sinusoidal signal. Here also I'll have the sinusoidal signal only, but both will be in phase. Okay, in phase in the sense there won't be any phase shift. Okay, so that is what that is why we call this as non-inverting terminal, and this is said to be the inverting terminal because when you ground this non-inverting terminal and when you apply voltage to the inverting terminal, the output will be out of phase. Out of phase in the sense it will have 180 degrees phase shift. Okay, so here I'm giving the input in this way. Okay, and at the output my output will be inverted. So this is how the output will be. It will be amplified, but it will be inverted. So inverted in the sense we will consider it to have 180 degrees out of phase, 180 degrees phase shift between input and output. Okay, so that is what the op-amp. And as I've mentioned, it is a IC. It is available in the form of IC741. Okay, where it consists of 8 pins. Okay, the first pin is offset null. Second one is inverting terminal. Whatever negative I was saying, no, like that negative terminal. The inverting terminal is at the second pin. Third pin, non-inverting terminal, minus VEE plus VCC. This is to bias the op-amp is again made up of transistors only. So in order to bias, we will be providing this minus VEE and plus VCC. Okay, and then output will be taken at pin 6. Okay, and fifth one and the first one is offset null, and to the 7th pin will give plus VCC. Okay, plus VCC minus VEE for biasing the op-amp. Okay, why we need to bias the not the op-amp, it is a transistor. Okay, transistor should be biased in the proper way so that the conduction will happen and it will be able to amplify the signal. Okay, so that is what that is why we will provide the biasing. So minus V and plus VCC are nothing but the biasing inputs. The biasing inputs in the sense, see, you need to provide proper voltage between the input and the output so that it will amplify the signals properly. So that is what the biasing. Okay, so plus VCC minus VE or such kind of input voltages, and 8th pin will not connect anything. Here offset null, first pin and the 5th pin are offset null. Offset null in the sense, see, actually, if you don't provide any input to the op-amp, so this is my op-amp. Here, if you don't provide any input, in the sense V1 is equal to 0, V2 is equal to 0, what will be the difference between that? It will be 0 only. So that is provided to the op-amp. So what this op-amp will do, it will take the difference between these two and it will amplify. Here the input itself is 0, so the output should be equal to 0. Ideally this will happen, but practically it will not be equal to 0. You may have some output voltage. It might be due to the due to some mismatch in the input circuit. So that is the reason you may have some output voltage here. Okay, so that output voltage will be made equal to 0 by setting this offset null. Or in other way, both V1 and V2 common mode signals. These are said to be the common mode signals. V1 is equal to V and V2 is also equal to V. Both are given with the same amplitude. Okay, so same signals are provided at V1 and V2. So what happens? The difference between that will be equal to 0. So the output should be equal to 0. But practically what happens? It will not be equal to 0 because it will also take the average between this V1 and V2. Okay, so that the signal will be amplified. Okay, so in order to make the output equal to 0, we will provide some input voltage that is said to be the offset null voltage. Okay, ideally this offset null voltage should be equal to 0. Okay, the reason behind that is ideally what should be the output? If both the inputs are same or both the inputs are 0, the output should be equal to 0. Ideally, if you are getting 0, you need not adjust this offset null. But practically, since it is not happening, what we'll do, we'll adjust this offset null. Okay, so that offset null, we are not adjusting in the sense offset null voltage value will be equal to 0. If we are adjusting in the sense, it will have some value. Okay, so ideally the offset null voltage should be equal to 0. Okay, so this is what like I see structure and how like what are the different inputs and how it is providing the output. Now coming to the differential, see, we can operate this op-amp in 3 different modes. Okay, one is the differential mode, the second one is double-ended differential mode, and the third one is common mode. Common mode, as I've already explained, both V1 and V2 will be provided with the same input. Okay, same input. V1 and V2 both inputs will be given with the same signals. Okay, here if I'm giving 5 volts peak-to-peak signal, here also I'll give 5 volts peak-to-peak signal. Okay, common mode in the sense both the inputs values will be equal to same. So in that case here V0 will be equal to, see, generally V0 output V0 is nothing but, as I've already mentioned, this op-amp what it will do, it will take the difference between these two and it will amplify. So let me write that amplification factor. This A is nothing but the amplification factor or the gain. Okay, gain, voltage gain. Okay, A is said to be the voltage gain into VD. Okay, so this is how we generally calculate output. Okay, so V0 will be equal to A into VD. VD is nothing but difference between the input signals. VD is equal to V1 minus V2. So V0 should be ideally equal to 0. Okay, ideally it should be equal to 0, but as I've already mentioned, it will not be equal to 0. Practical case, it will not be equal to 0. It will, along with the difference, it will also take the average between these two inputs and it will amplify that as well. In order to make that output voltage is equal to 0, we will reset the offset null voltage. Okay, we will give some particular voltage so that the output value will be equal to 0. Okay, so this is what the common mode gain. Common mode connection. Differential mode in the sense either will give input to the inverting terminal. See, negative is inverting terminal. Inverting, the meaning of the inverting I've already explained you. Plus is non-inverting terminal. Okay, non-inverting terminal means it will not invert the output. Okay, however the input is given, the output will also be in the same way but amplified. That is the only difference. Okay, so in the differential mode, either you will be giving input to the inverting terminal or to the non-inverting terminal. To either of that, you will give the input so that you will calculate the output. So generally, how will you calculate V0? V0. Let me consider first I am giving the input to the inverting terminal. So V0 will be equal to A times of non-inverting terminal voltage Vn minus Vi. Okay, Vn is nothing but the non-inverting terminal voltage minus Vi. Vi is nothing but the inverting terminal voltage. So V0 will be equal to A times of Vn. Vn is grounded. So if I connect like this, see, connecting like this indicates it is a grounded connection. So grounded, it is grounded, in the sense the voltage there will be equal to 0. Minus here, if you observe, it is connected to the some input signal. So V1. So V0 will be equal to what? Minus AV1. Okay, so if you just observe, you are getting a negative symbol. This negative symbol indicates 180 degrees phase shift. And here I am getting 180 degrees phase shift because the input is provided to the inverting terminal. Okay, whenever you provide input to the inverting terminal, my output will be 180 degrees phase shift. So that this negative sign indicates that 180 degrees phase shift. The same thing, differential mode. Even this configuration is a differential mode configuration only. Here what we are doing, this is the inverting terminal. And one more thing, I will just give you one suggestion. Always take the negative sign up. It's not mandatory, but for the analysis purpose, it will become very easy for you. Okay, always try to take this inverting terminal towards upside and the non-inverting terminal down. Okay, why? I will tell you the reason. Okay, later I'll tell you the reason. Okay, so even if you connect in the other way, it's not a problem. But if you connect in this way, it will become easy for you to remember the circuits. So that's why I'm telling you. Okay, fine. This is the non-inverting configuration. Non-inverting configuration in the sense we are giving input to the non-inverting terminal. This is an inverting configuration. This is the inverting configuration. I will write the full name only. Inverting amplifier. Inverting amplifier mode. This is non-inverting amplifier mode. Non-inverting in the sense non-inverting amplifier mode in the sense, like it will be providing the input to the non-inverting terminal and the inverting terminal will be grounded. Whichever is grounded, that is said to be whichever is grounded, the other terminals mode will call. Okay, so if you just observe, negative terminal is grounded, in the sense negative is grounded, inverting terminal is grounded, or you can see in the other way, non-inverting terminal is provided with some voltage. Okay, so this is the non-inverting configuration. Again, V0 you need to find. V0 is nothing but A times of Vn, non-inverting terminal voltage, minus Vi. Vn is nothing but V1 minus Vi. Vi is nothing but 0. So it is nothing but AV1. Okay, V0 is nothing but AV1. So if you just observe, it is amplifying the signal. Okay, but it's not phase inverted. See, in the previous case, I've got minus sign, but if you observe here, it is plus only. Plus indicates it is in phase. Okay, so this is what the differential mode. Then comes the double-ended differential mode. Double-ended differential mode in the sense you will provide different input for inverting terminal and as well as the non-inverting terminal, and difference between those two will be taken and it will be given to the op-amp. This is nothing but your op-amp, that will be given to the op-amp, so that your V0 will be equal to A times of V1 minus V2. Okay. So this is a double-ended differential mode. So the main thing here, what you need to concentrate is the first one and the third one. First one and third one are very, very important. Second one is also important, but here you need not analyze much. Okay, what you are doing, you are providing V1 signal, V2 signal, and you are taking the difference, and that difference will be amplified. Okay, so that is what your double-ended differential mode configuration. Okay, coming to the equivalent circuit. Okay, coming to the equivalent circuit, this is what the equivalent circuit. Equivalent circuit of an op-amp. Okay, so this is my VI, let me write as VI only, this let me write as VN only. So this is the op-amp, and op-amp, it is given to the this is the input side and this is the output side. Okay, so input side, what we are doing, see, always whenever you have any amplifier circuit, as you see from the terminals, the impedance is represented as Zi. Zi is said to be the input impedance. See, all this parameters, ideal op-amp characteristics are very important. Ideal op-amp characteristics. Ideal op-amp characteristics are very important. Okay, so in the exam recently, the other section, in the sense, ERS is physics cycle, right? Whatever exams you have written recently, it is a physics cycle. So the chemistry cycle people have written the exam. Okay, in that exam, they have asked you ideal op-amp characteristics, and I'll tell you, most of the students, I went for valuation. Okay, so most of the students have cleared their subject just because of this module. This module, they've got almost 20 marks, right? So 20 marks, maximum people have scored 20 out of 20 in this module. Okay, it's very simple. That's why I thought I'll teach you this module first. Okay, so in that they have given ideal op-amp characteristics, which they have given for 4 marks. 4 marks directly you'll get, and there you have to just specify what is the input impedance. I'll tell you the parameters. Okay, so all that parameters, even if you are if you have written 4 parameters, I have given marks. Okay, 4 parameters, 4 marks I have given. Okay, so this is very important. Okay, so this is the ideal op-amp equivalent circuit. So this, as you see from this terminals, this input impedance is given by Zi, and at the output side you will have the AVD, because at the output you need to get the amplified signal. So AVD in the sense A times of V1 minus V2. Okay, V1 minus V2, and as you see from the output terminals, the output impedance is Z0. Z0 is the output impedance. Zi is the input impedance. Input impedance. Okay, so ideally the Zi should be always equal to infinite. Input impedance should be equal to infinite. Okay, only when your input impedance is equal to infinite, whatever input you are giving here, that will be appearing across the amplifier circuit. Okay, so that's why always Zi should be infinite. In the same way, Z0 is the impedance, as you are seeing from the output terminals. Okay, so Z0, if you have Z0, what happens? Z0 is nothing but the resistance. Resistance or impedance. So what happens? There will be some voltage drop across this Z0 also. Okay, so if you don't want to have any voltage drop across Z0, so whatever output that will be reflected in this AVD. Okay, so if you want to get the complete output voltage, yes, Z0 should be equal to 0. So how to remember? I'll just give you one small hint. Okay, so if you just see the op-amp circuit or any amplifier, we'll just represent it in this way. Okay, any amplifier circuit will just represent it in this way. So this, if you see, I have a big line here. So this Zi will be equal to infinite. Input impedance will be equal to infinite, and if you see at the output side, this is my output side here. I'll take the output. Okay, so if you see at the output side, it is like just a point. So yes, Z0 should be equal to 0. I'm just telling you how to remember it. And in the exam, most of the people, what they have done is they have just drawn the symbol. Okay, they have just drawn the symbol, something like this. Okay, maybe V1, V2, this is my output. Okay, even if you don't specify plus VE and minus VE, plus VCC and minus VE, it doesn't matter. But this rest, all the three terminals should be there, like this terminal, and this terminal should be there. compulsorily. Even if you don't connect plus VCC and minus VE, it's okay, no problem. But this should be there. Along with that, people were forgetting which is the inverting terminal and which is the non-inverting terminal. If you don't write this, the complete thing will go wrong. Okay, because this based on this only the complete circuit will be analyzed. Okay, so this whatever plus minus you have, this inverting and non-inverting terminals you have to definitely write that. Okay, it is very important. Okay, don't miss this. Okay, and symbol also, like people were drawing different ways. Okay, they were drawing whatever they want. Okay, just like this without any inverting non-inverting terminals shown. Okay, this is how they have written. So this is not right. Okay, always these three terminals are must along with the plus and minus sign within the op-amp. Okay, so this is very important thing to be noted. Okay, hope you people are following, right? Are you able to hear me? Okay, fine. So these are the two parameters. Along with that, we'll see some other parameters also. And here, one thing what we need to note down is, like, see, as I'm varying input, V1 and V2 are provided as inputs to the op-amp. So what happens? The difference between these two will be taken and it will be amplified. VD. Okay, so as you increase the voltage, VD will also increase. What happens? Even this V0 will also increase. Okay, so what happens is it will just increase as you are increasing the input VD. Your V0 will also increase. Okay, so it will not go to infinite. So what happens? After a certain time, it will saturate the values. Okay, how much ever you are increasing the difference VD is increasing, still it will be, the output will be constant. Okay, so still the output will be constant. In order to avoid that, we will take the feedback. Okay, feedback in the sense, feedback is nothing but part of the output will be connected as an input to the input terminal. Okay, so this is how we will connect from output, it will be connected to the input. Okay, so if you just observe, V0 is given to the non-inverting terminal. If V0 output is fed as an input to the inverting terminal, then it is said to be the negative feedback system. Negative feedback system. Or you can give another feedback system which is said to be the positive feedback. From output it will be fed as an input. Okay, so here if you just observe, the output is fed as an input to the non-inverting terminal. Here if you connect it to the inverting terminal, we'll call it as negative feedback. If we are connecting it to the positive terminal, then we'll call it as positive feedback. The reason why it is called as negative feedback when we are connecting it in the other way, here if you connect it in this way, it is said to be the negative feedback. Okay, why we are calling it as negative feedback in the sense, here V1 is there. Okay, along with that, even this V0 is fed. Okay, so what happens here, both the signals will get subtracted here when you are giving it to the non-inverting inverting terminal. Okay, so both the this input V1 and whatever is fed back, it will get subtracted. So since it is getting subtracted, we call it as negative feedback. In the other way, if you are giving it to the non-inverting terminal, here what happens, both will be in phase and both will get added. So that is the reason we call it as positive feedback. Okay, but with the negative feedback will be used in amplifier circuits, and positive feedback will be used in oscillators. Negative feedback will be used for amplifiers and positive feedback will be used in oscillators. The reason behind why we will go with the negative feedback for amplifier circuit is it has so many advantages. Advantages like bandwidth will be improved. So like you'll have high bandwidth. Okay, and see, as I've mentioned, the input impedance Zi should be equal to infinite, right? So if with the positive feedback, your Zi will be more, Zi will increase. Okay, Zi should not be less. Zi will be increased with negative feedback. Okay, and even Z0 should be 0, right? So with the negative feedback, this Z0 will be reduced. Okay, I see these are whatever I am giving here, these are the ideal values, but practically these won't be the values, right? So for the practical circuits, when you give the feedback with the negative feedback, you're getting more advantages. Okay, so few of the advantages what I have listed here is bandwidth will be increased with negative feedback, and Zi will also be increased with negative feedback. Z0 will be decreased. All these are advantages for the op-amp. Okay, so with the negative feedback, you'll have all this. Okay, so that is the reason most of the amplifier circuits will go with the negative feedback system only, negative feedback itself. Okay, so the reason behind that is I've just listed few advantages here with the negative feedback. Okay, so positive feedback will be used for the oscillators. Okay, oscillators is nothing but it is a circuit. Even on oscillators, you have lots of questions in the exam. Okay, so oscillator, it is a circuit that provides sustained oscillations. Sustained oscillations in the sense you will have the sinusoidal signal with constant frequency and amplitude. Okay, so it will provide you the sustained oscillations. If you want to get the sustained oscillations, then we'll go with the positive feedback. So how it is going to provide sustained oscillations, all that we'll see in the next coming modules. Okay, here I'm just telling you why we are going with the positive feedback and why we are going with the negative feedback. Okay, so this is these are some parameters related to the op-amp, and here for the amplifier circuit we will always take negative feedback. Okay, so in order to achieve the proper amplification, we'll go with the negative feedback. Okay, so these are the few things that you need to note it down. And coming to the internal diagram, so if you just recall, in the previous class I've shown you the internal diagram where the diagram is so complicated, it has lots of transistors and all. So here you need not study all that. Here what we'll do is we will just see the block diagram representation. Block diagram of op-amp. Sometimes they may even ask a question related to this. Anyway, for you, as they have cancelled the exam, you can concentrate with your internal exams. Okay, so in exams, as I've already mentioned, they may ask you explain block diagram of op-amp. Okay, so in that case, it will have 4 stages. This is a block diagram representation. So first, this entire thing is nothing but the op-amp. This entire thing is nothing but the op-amp which we were representing. Okay, so op-amp, as you know, it will take 2 inputs. Okay, so first this block, I'll name it as input stage. Second block is intermediate stage. Level shifting stage, and the last one is output stage. Okay, so first input stage, what it will do, it will take 2 inputs and it will also provide 2 outputs. Okay, so that is the reason this input stage is said to be the dual input balanced output. Input stage, it is the dual input and balanced output amplifier stage. Okay, it is a differential amplifier which amplifies the difference between the 2 input signals, and it will provide the output. Okay, and it also decides the value of input resistance, which ideally it should be 0. Infinite. So this input stage, it is said to be the dual input and balanced output amplifier stage, and what it will do, it will take the difference between these two it will take the difference between these two, and that difference will be amplified here, and it will provide you two outputs. Okay, and here this input stage will also take care of this Zi. Okay, ideally the Zi should be infinite. Okay, so what this input stage will do, along with providing the amplification between the two input signals, it will also provide, it will also increase the input impedance. Okay, that is what for this input stage is used. Okay, then now what we are doing, we are giving it to the intermediate stage. This intermediate stage, again, it is an amplifier itself. Okay, what it will do here, it will take two inputs and it will provide one output. That's why this is said to be the dual input, single output, dual input, unbalanced output. This intermediate stage, it is dual input and unbalanced amplifier stage. So what happens here is, it will take two inputs, okay, but it will provide only one output. Okay, so this is the that's why it is said to be the unbalanced. Okay, unbalanced word is given because it is taking two inputs, but it is providing only one output. So again, this intermediate stage also, it will take the difference between these two and it will amplify it. Okay, and it will amplify the signal, and this intermediate stage will provide additional gain. Okay, here this input stage will provide some gain. Again, let me consider the gain is A1. So this the second amplifier, intermediate stage amplifier, even this has to provide some additional gain, which will be A2. Okay, so additional gain will be provided by this intermediate stage amplifier. Then comes the level shifter stage. Okay, so here it will not amplify anything, but what it will do is, if the signal ground point is changing, okay, instead of having the signal in this way, if its offset voltage is increased like this, then what it will do, it will bring back to the ground level. So this is what the use of the level shifter stage. Okay, then comes the output stage. Okay, so output stage, again, it will amplify, it will help in the amplification. Okay, again, it will provide very high gain. Here I'll get output V0. Again, this output stage will provide high gain, and this along with providing the high gain, it will also control the output impedance. It will also provide the output impedance. Okay, the resistance here will be output resistance will be decreased by this output stage,